This is the Hess's Law video. Hess's Law states that if a chemical equation can be written as a sum of several other chemical equations, the enthalpy change of the overall chemical equation equals the sum of the enthalpy changes of the individual chemical equations. This sounds like a lot, but what it's really telling you is this. If you have a chemical reaction that takes place in many steps, if you add up all the steps, that gives you the total energy change. Let's see this in action. Here we have a two-step reaction, step 1 and step 2, and we know the energy change of the two steps. If we want to find out what the overall energy change is, and the overall reaction is, then we need to add them up. So over here on the left side, we have the reactants. We have 1 and 2. We have 3 hydrogens here, plus 4 more here. We have 7 hydrogens. And we have 2 NO2s. On the right side, we have 2 ammonias, 1 nitrogen, and 4 waters. Now when you're done adding these together, you're going to notice that on this side and this side, you have N2. We can cancel these because they're exactly the same on both sides. So when we're done canceling them out, our reaction is 7H2 plus 2NO2 yields 2NH3 plus 4H2O. Now it really doesn't matter what order you do the reactants in and the products. So if we wanted to say 2 NO2s plus 7 hydrogens yields 4 waters plus 2 ammonias, that would be okay. Since we added up these two equations, we're also going to add up the 2 enthalpy change signs. This is enthalpy, or for our purposes, it's also equal to energy because we have a constant pressure. So our delta H value is negative 98 plus a negative 340, which is negative 438 kilojoules. Now there's other ways that Hess's law can be used. It can be used, for example, when we're trying to find out a chemical equation and we have some other reactions that we know, but we might need to move them around, manipulate them, make them work. So what does that mean? I'm going to move this up here to the top. This is our target equation. This is what we're trying to find out. These are equations that we've been given. We know them from previous experiments, but they're not necessarily in the order we want them to be in. Let's start at the beginning. To start with, we want to have 2 NOCLs as reactants. And when you look down here, the only place we have NOCl is right here. So we're going to call this equation number 2 and equation number 1. So what we're going to do with our equation number 2 is we're going to flip it. We want the 2 NOCLs to be reactants and not products. So I'm going to rewrite the equation exactly the reverse of what we have right now. Since we're doing the reverse reaction, the value for our enthalpy or energy also has to be flipped. So negative 103.4. Whatever you do to the reaction, make sure you do it to the enthalpy sign as well. Okay, the next thing is we want to have 2 NOs as reactants, as products. So when we look, NO is located here, and it's the only place that we see it. So this tells us my 2 NOs that I have here as reactants, I want to make them as products. To do that, I want to take that equation and I want to flip it around so that this is on the correct side. Since when I flip that, I will also have to change the sign for the heat or the enthalpy. So it's now going to be a positive, not a negative. I also wanted to have chlorine as a product, And right here I have chlorine as a product. So I'm going to go ahead and leave that there and see how it works out. I'm going to take these two equations, I'm going to add them together. Now, if there is anything that's exactly the same on the left and the right, I can go ahead and cancel it out. So I have N2 here and here. It is exactly the same and the same amounts. They're both 1 and 2s. So I can cancel them out. I also have O2 here and O2 here. They're exactly the same on both sides. I can cancel that out. That leaves me with 2 NOCLs as reactants, yields 2 NOs, and a Cl2. This exactly matches my target equation. So I'm going to add up my two reactions here. I have the 180.6 plus the negative 103, and this comes out to be a positive 77.2 kilojoules that's being released as heat. Let's try another one on the back. I have my target equation. This is what I'm trying to find out. 2 carbons plus a hydrogen makes C2H2. What is my energy change? These are my 3 equations. I'm going to go ahead and number those so I can use them down below. Starting at the beginning, I want 2 carbons. Down here I have 2 carbons on this side, and it's the only reaction where I have carbon. It's on the correct side, so I don't need to flip it, but I want to have 2, and I only have 1 down here. So this whole equation, I'm going to times it through by 2. When I do, I get 2 times 1, 2 carbons, plus 2 times 1, 2 oxygens, yields 2 times 1, 2 carbon dioxides. My delta H value, I also have to multiply it through by 2. So instead of being 393, it's going to be a negative 787 kilojoules. Now let's go to the next one, the hydrogen. I want to have 1 hydrogen as a reactant. So I'm looking for hydrogen by itself, and the only place I see it is right here. It's already a reactant, and there's already 1 of them. So equation number 3 is perfect. There is nothing I need to do with it. So I'm only going to write it down and record my heat or enthalpy change. Notice that I did not change the reaction, so I do not change the delta H either. Last step, I want to have 1 C2H2 as a product. Here I have it as a reactant. It's on the wrong side but the right amount. So I'm going to take it and I'm going to flip it. So all my products will become reactants, and all my reactants become products. Since I have flipped the equation, I'm also going to flip the sign. So now I'm ready to add up my equations together and get my overall heat change. So let's change my color to make my work easier to see. I want to look for anything that's the same on both sides. So right here I have 1 H2 and 1 H2, so that can cancel. Over here I have 2.5 oxygens. Here I have 5 half oxygens. It's the same as 2.5, so they're going to cancel. I also have 2 carbon dioxides. They can cancel. When I'm done, I have 2 carbons plus a hydrogen yields C2H2, ethine. My delta H is going to be the sum of all the steps. So you see how we're adding up all the steps? We add up all the heats, and we get a grand total of 226.7 kilojoules.